Mankind's first great mystery was understanding the motion of objects in the sky, solved by Newton. The second great mystery was understanding the nature of light, solved by Maxwell. Maxwell's four equations explain all electrical and magnetic phenomena, including electromagnetic radiation, which includes light. A brief but fascinating history of the development of Maxwell's equations is given in an online article, The Long Road to Maxwell's Equations, and there's a link in the description below. While the development of the equations took 100 years, as the article details, we can now see that they follow directly from the analysis of simple experiments. We'll briefly review the experiments and the equations that summarize their results. The equations can be written in integral form and in differential form. We'll start with the integral form, as the experimental results correspond to the equations in integral form. The third and fourth equations are the basis for the analysis of electromagnetic radiation, and we'll derive the differential form for these equations in the next video. Maxwell's first equation is equivalent to Coulomb's law of force. The early Greeks noticed that when a rod of amber, the Greek word is electron, was rubbed with fur, it would then attract small bits of paper or other light materials. Experiments with static electricity continued through the centuries and were finally quantified by Charles Augustin de Coulomb, a French physicist in the 18th century. When amber is rubbed with fur, it acquires an excess negative charge. If the amber then touches a small bit of paper, some of the negative charge will be transferred to the paper. When glass is rubbed with silk, it acquires an excess positive charge. If the glass then touches a small bit of paper, some of the positive charge will be transferred to the paper. Coulomb did these experiments and measured the forces between the bits of paper. He observed that like charges repel and unlike charges attract, and he summarized the results in Coulomb's law of force, which states that the force between two electrically charged objects is given by 1 divided by 4 times pi times epsilon sub 0 times the product of the charges on the particles divided by the distance between the particles squared. Epsilon sub 0 is a constant, the permittivity of free space. This is our starting point. We can imagine that a charged particle creates an electric field that extends outward from the particle as shown in the diagram. The magnitude of the electric field at a distance r from the particle is given by 1 over 4 times pi times epsilon sub 0 times q, the charge on the particle, divided by r squared. When there are two or more particles, the fields add. From Coulomb's law of force, we can evaluate the surface integral of the electric field over a sphere of radius r surrounding a charged particle at its center, as the field is constant on the sphere. It can also be shown that the value of the integral is the same for any closed surface enclosing the charged object. This is Maxwell's first equation in integral form, and it states that the surface integral of the component of the electric field perpendicular to the surface equals the sum of the charged particles enclosed by the surface divided by epsilon sub 0. A dielectric material, or dielectric for short, is a substance that is a poor conductor of electricity, but that provides a good support for electric fields. For example, free space. Electric fields can exist in dielectrics, and electromagnetic waves can be propagated in dielectrics. Examples of solid dielectrics include porcelain, glass, and most plastics. In addition to the E or electric field, we will also be discussing the D field or electric flux density field, and it's also sometimes called the displacement field. Here the terminology is a little confusing. Normally a flux is used to represent a rate of flow of fluid, energy, or particles, and more generally to be in a state of flux means that things are changing. But here nothing is changing, nothing is flowing, everything is static, and yet we are speaking of electric flux. So what is the D field or electric flux density field? The diagram shows a capacitor with an air gap between its plates and a capacitor with a solid dielectric between its plates. When the charge on the capacitor creates an E field between the plates, the D field in the top capacitor is given by epsilon sub 0 times E. So the fields are collinear, but they have different magnitudes and different units. When there is a solid dielectric between the capacitor plates, as in the bottom capacitor, the polarization of the dielectric material will create an induced electric field that opposes the E field generated by the plates, and the D field is formed as the sum of the original E field and the induced E field. The formula for D, the electric flux density, is D equals epsilon sub 0 times 1 plus chi, where chi is the electric susceptibility of the dielectric, times E. In homogeneous, isotropic materials, chi is a number. In non-homogeneous, non-isotropic materials, chi is a rank 2 type VC tensor, and chi can also be frequency dependent. When chi is a rank 2 tensor or frequency dependent, it introduces significant complications into the model which are beyond our scope. So for us, chi is a real number, and 1 plus chi equals the relative permittivity, epsilon sub r, and the D field is given by epsilon sub r times epsilon sub 0 times the E field. So again, it is collinear with the E field and equals a constant times the E field. Current flowing in a wire creates a magnetic field surrounding the wire, as shown in the diagram. The orientation of the magnetic field can be determined by using the right-hand rule. That is, by grasping the wire with the right hand and with the thumb pointing along the direction of current flow, your fingers will be circling the wire in the same direction as the magnetic field. There is a magnetic flux field B and a magnetic field H. However, both are commonly referred to as the magnetic field. The relationship between them is, in free space, B equals mu sub 0 times H, where mu sub 0 is the magnetic permeability of free space. In a dielectric, the equation is B equals mu sub r times mu sub 0 times H, where mu sub r is the relative magnetic permeability of the dielectric. For us, mu sub r will always be 1. Note that the magnetic field lines are closed, unlike the electric field lines that radiate outward from electrically charged particles. Maxwell's second equation states that there are no sources of magnetic field lines, that is, no magnetic analogs to electrically charged particles. Written in integral form, the equation states that the surface integral of the component of the magnetic field perpendicular to the surface over any closed surface is 0. That is, the magnetic flux going into a closed surface equals the magnetic flux coming out. An inductor consists of multiple loops of wire around a common core. If there are 20 loops, the magnetic field in the core is 20 times as strong as the magnetic field around a single wire. By placing two inductors on a single core in close proximity, the magnetic field generated by the inductor on the left will extend through the interior of the inductor on the right. So Faraday placed two inductors as shown in the diagram, and by closing the switch on the left or active inductor, he created a changing magnetic field that extended through the core of the passive inductor on the right. He observed that the changing magnetic field in the passive inductor produced an electromagnetic force, i.e. a voltage, in the inductor and a resulting current. So he conjectured that a changing magnetic field produces an electric field, and he formulated Faraday's law of induction that states that, given a path C that encloses a changing magnetic field, the line integral of the dot product of the E field and the differential line element, that is, the induced voltage in the loop, equals the rate of change of magnetic flux in the enclosed field. To make the units match, Faraday defined the unit of magnetic flux, the Weber, to be the amount of flux that, when enclosed by a path consisting of a single loop and reduced at a constant rate to 0 in 1 second, produces an induced voltage of 1 volt. Note that Faraday could control the rate of change of magnetic flux by controlling the current in the inductor on the left, and he could measure the voltage in the circuit on the right, so the equation corresponds directly to the observables in the experiment. This is one of the two equations that govern electromagnetic radiation. The existence of the magnetic field surrounding a current-carrying wire was discovered by Danish physicist Hans Christian Ørsted in 1820. As he was giving a lecture and demonstration of electrical effects, he noticed that an electric current in a wire caused a compass needle to deflect. Until that time, there was no known connection between electricity and magnetism. Ampere picked up the ball from there. Using a compass, he traced out the shape of the magnetic field around the wire, as we have seen, and he also discovered that two wires carrying current exert a force on each other due to their magnetic fields, and by experimenting with two wires, he was able to determine the strength of the magnetic field given by the equation: the magnitude of B equals mu sub 0, the magnetic permeability of free space, times I, the current, divided by 2 times pi times r, that is, the circumference of the circle. Thus, if the path C is a circle with the wire at its center, the magnitude of the magnetic field is constant on C and points in the same direction as an infinitesimal line element. So we have the contour integral of B dot ds over C equals mu sub 0 times I. By a geometric argument, it is easy to show that the equation is true for any path C enclosing the current-carrying wire. A changing current in a wire segment containing an air core capacitor, as shown in the diagram, will result in a changing magnetic field around the wire. Maxwell noted that the magnetic field surrounding the wire was the same as the magnetic field surrounding the capacitor. However, given the path C, as shown in the diagram, it does not enclose any current whatever, and yet the magnetic field around this path equals the magnetic field around the rest of the wire. To account for this, Maxwell added a second term, shown below, to Ampere's law, so that now the contour integral of the dot product of the magnetic field and the line element equals mu sub 0 times the enclosed current plus the new term, mu sub 0 times the rate of change of the enclosed electric flux, phi sub d. This addition is the key to electromagnetic radiation. From Faraday's law, a changing magnetic field produces an electric field. And with this addition to Ampere's circuital law, a changing electric field produces a magnetic field. The two fields in tandem constitute electromagnetic radiation. The assignment is to review Maxwell's equations in integral form, in particular equations 3 and 4, the ones we will use to generate electromagnetic waves. Also, the units for electricity and magnetism are probably new to you, and there are many ways to convert them, and they can be confusing, at least they were to me. So I compiled this summary for my benefit, and I'm including it in the notes for your reference. I suggest going to the class notes and printing these pages so you can refer to them as needed.